Hello, everyone. Welcome to another topic in chemistry. Our topic today is it's three little topics: the photoelectric effect, lasers, and the Doppler effect related to light. So if you are watching these video notes on the day they were first assigned, this is part of Unit 7. It's kind of like 4A. It's like just a little extra add-on. Go ahead and start setting up your focused notes page. The essential question we're going to answer today is: how are the photoelectric effect, lasers, and the Doppler effect all related to light? If you're watching these video notes on any other time, welcome. I'm excited to explain these things to you. Again, the focus is the photoelectric effect, lasers, and Doppler effect, assuming you already know some things about wavelength and frequency and energy and how electrons move up and down between energy levels to create light and waves and all of that stuff. This is just kind of the last few little topics related to the chemistry of light. All right, let's get into it. Let's start with something called the photoelectric effect. The photoelectric effect, I'm going to start with the conclusion that came from studying this photoelectric effect. What it does is it describes light as quantum of energy particles instead of thinking of light as a wave, which is what we've been doing the whole rest of the unit. So think of like little pieces of energy that come out from a light source, and those are called photons. So instead of it being a wave pattern, there's like little pieces of energy, and those are referred to as photons. A photon is just a small amount, some measurable amount of light energy. So that is what the focus of the photoelectric effect is. So we're not thinking about light as waves, we're thinking about light as energy, like little pieces of energy, actually. So I start with the conclusion because that kind of helps set up the rest of what I want you to know. So here's what the photoelectric effect does. It says that electrons are ejected by metals when certain light shines on them. Okay, now that sounds really like amazing and special and wild, but think of it, this is solar panels, right? Solar panels work because whatever metal that is being used, UV light from the sun shines on it. That has enough energy to move electrons in the atoms of those metals. And then as the electrons move, that's what electricity is. So then it creates a circuit. So that's what the photoelectric effect is, what solar energy is based upon. But it only works with certain light and certain metals because of something called the threshold of energy. The threshold of energy is sort of the boundary of energy between observing the photoelectric effect or not observing the photoelectric effect. So you have to be above a threshold of energy to actually observe electrons being ejected by different light. So if it's below the threshold of energy, like for example, let's say we had a sodium panel and red light was shining on it. Well, we know that red light is our lowest energy of light that we can see. So what this is saying is that nothing will happen. The red light will just shine on the sodium. The energy gets absorbed, but nothing happens. Nothing else happens. So that's if the light being shined on the metal is below the threshold of energy, you don't see anything. So if it's above the threshold of energy, this of course is what we are hoping for because this is interesting. So if you took that same sodium panel, but now you shine green light on it, or in this case, the picture has blue, but green light is a little bit higher energy. So red was not high enough, but maybe green is high enough so that when green light shines on sodium, those absorbing of the energy, it's enough to actually move the electrons between the atoms in the panel and the panel of the metal, and it actually ejects those electrons, moves them, and then that can create electricity. And then if green light worked, then of course blue would also work, but it would change how those electrons are moving. So if you take green light, so if green light works, but now you make it a higher frequency, so let's say I change it to blue or violet, you get a higher velocity or speed of the electrons ejected. So in this case, like, okay, so this amount of light, this is of course arbitrary, produced 3 electrons. This amount of light will still produce 3 electrons, they'll just move a lot faster. So that's the idea. The other option is, well, what if I take my green light and I know that that's above the threshold of energy and I keep it green, but I make it more intense green. So like a brighter green light, what would happen then, instead of just like these 3 electrons going at some speed, maybe you get 10 electrons at that same speed. So frequency is related to speed, and then intensity is related to the amount of electrons that would actually be ejected. Now, I actually have a pretty good simulation that I can use to represent that. So I'm going to do some clicking in and out of my screen here, so just kind of bear with me while I get organized. But I want to show you a pretty good simulation of the photoelectric effect. So what I have here is kind of a system of a circuit. Here's light that's shining on it. The metal that I've chosen right now happens to be sodium. You can toggle between other things. If you're curious, you can find this online. PhET simulation called Photoelectric Effect. And so I've got sodium that is being shined on. The red light is what I have right now. Intensity is at 50%. And then we'll hit play. So you can see that this is trying to produce some type of current, right? It's trying to produce an electric current. But what we see is that the red it's not enough to do anything. So nothing is happening. So if I increase my frequency to orange, let's see if anything happens there. Nope, not so much. How about yellow? Nope, I'm still not getting anything. What if I start going to green? Nope, not yet. So I'm not above that threshold. There we go. So this amount of energy is enough to make the electrons start to eject from the sodium. So that's the idea here. So green light is enough to create that circuit and connect these two panels. And then if this was set up to actually collect data, then you would see these numbers. So just ignore this from now. So green light is above the threshold of energy for sodium. So now these electrons are actually being transferred in this system. So green light works. Okay, so that means that if I increase the frequency, what I should see is electrons coming out faster. So not more electrons than there were. So these slow ones are the green light, and then you see the faster ones. So then the other option is that I can keep it this blue light, but I can increase the intensity. And so now you start seeing more electrons coming out each time, but about the same speed as they were before. So that's kind of the idea of the photoelectric effect. So this is basically what solar panels are used on. So when people are building solar panels, they are choosing metals that can be excited by the UV light from the sun. And then that is what will move the electrons, create the circuit, and then that will cause, now you can see that the current is high enough because enough electrons have been moved. So that would be the thing that people would have to try to figure out when they are building solar panels. It matters what elements you use here because you want to get enough of a current for it to actually matter. So that is the photoelectric effect. All right, let me go back into here. And we already did all of this. All right, go ahead and write your level 1 question so far about photoelectric effect. Just thinking about this idea, what it means, a little bit like that. All right, the next thing I want to talk about is lasers. Did you happen to know that lasers is an acronym? Maybe you already knew this, maybe not, but since you know that lasers has something to do with light, go ahead and pause the video and see if you can predict what laser stands for. All right, let's see if you were correct. Laser is an acronym that stands for light amplification by stimulated emission of radiation. So here's a really good example of a pretty simple laser. So the idea is that you have some type of power supply which is going to amplify your light, it's going to stimulate your light so that it can be emitted. And then you've got these reflected mirrors that amplify it. So instead of it just being a light source that just goes right out the end of this kind of like laser gun, you've got these reflective mirrors that keep intensifying or amplifying that light that has been stimulated by your power supply. So some sort of electric source or power supply is giving energy to whatever sample you're using. So a ruby in this case. So the ruby crystal is being stimulated by the power supply. The light that the electrons are producing, because the electrons in the ruby are moving up and down, and when they come down, they give off energy. That light is being amplified, and then the radiation is being emitted out the end, and that's your laser beam. So that's what a laser is, related to light and electrons and those kinds of things. And then, of course, now that that's a really, really intense beam of light, that's an intense beam of energy that can be used for cutting, very precise, small things. It can get into small places, high energy, quick things for cutting. So that's kind of the benefit of that. And that's it. That's all I have on lasers. So go ahead and do your level 2 CASTA question. All right, and then the last thing I want to talk about is the Doppler effect. So the Doppler effect you might have heard of related to sound. It's that thing where, like, if you're standing on a sidewalk and like a siren drives by you, or you're stopped at a stoplight in your car and a siren drives by you, it's that change of pitch that you hear because the sound waves are moving with the object. So that's the Doppler effect as related to sound. It's that that sound. Wasn't that an amazing impersonation of a Doppler effect sound wave? I think you loved it. Okay, but we're not talking about the Doppler effect related to sound, though the effect is similar. So the general idea of the Doppler effect is the apparent change of wavelength when an object is moving relative to the observer. So red shift happens if the source is moving away from the observer. So if we're talking about light, this would be that the idea is that the wavelength would appear longer if the object was moving away. And then the opposite would be if the observer is standing still and the object is moving closer, the light source would start to have a shorter wavelength. So if we could see it, it would be whatever original color it was, it would go more towards blues and purple. In this case, whatever original color it was, it would go towards the oranges and reds. And so that's sort of the idea behind the Doppler effect, which again is a little bit strange. So I have this little video really quick that just kind of gives you a visual of what that would look like. So go ahead and just watch this for just a few moments. Oh, just a second, we'll find it. Or maybe not. What's going on here?
Change in wavelength
there we go.
Also applies to light from moving objects. So imagine a star, let's say it's moving in one direction across the screen, and you notice that the light waves in front of the star are compressed to shorter or bluer wavelengths, while the light waves behind the star are stretched out to longer and therefore redder wavelengths.
Okay, so that's just a quick video. Sorry about the mess up at the beginning. But that's just a quick just video idea of what this would look like if you could see it versus hearing it. So this idea of shifting of the observed wavelength has to do with the fact that an object is moving. Okay, so why do we care about this? Here's my connection. The connection is between Doppler effect and astronomy. The Doppler effect is how scientists have concluded that the universe is expanding, which is a huge deal because it's hard to observe that if you're sitting in the middle of it in your planet. So here's how we know. We know that stars are made of hydrogen, and we can measure the spectrum of energy given off by hydrogen here in a lab on Earth. So this is what it would look like. So this is a spectrum of hydrogen. This is called a dark line spectrum because there's certain places where hydrogen is absorbing energy and then certain places where hydrogen is giving off energy. So that's the example of some type of lab spectrum measured here on Earth. Then we measure an observed spectrum from a star. So a star is giving off light from space. We can measure that spectrum in our lab on Earth from the sample that's giving off light from space, and we notice that it looks different. So this is the lab spectrum. This is the galaxy or the star that we're measuring, and you can see that normally the lines should be here, but now they're moved this direction towards the red end of the spectrum, meaning that it is longer than it is expected. This is called redshift, and since it's longer than expected, this means it's moving away. And then our conclusion is then the universe is expanding. Here's just a visual of it. So if we had no expansion and we're measuring, it could be radio waves or whatever else we're doing, so stationary galaxy, and if the galaxy is moving away with the expansion of the universe, then those radio waves that were measured, those would stretch out longer, and then you end up with seeing that redshift that way too. So just another kind of visual of why we care about the Doppler effect related to light. All right, so now that we're talking about space and astronomy, maybe you can make a connection with that with your level 3 question to kind of end these notes. All right, so that brings us to the end of Unit 7, not just the end of these notes, but the end of your new information for Unit 7. So here would be your to-do list. So all work for Unit 7 should be done at this point. All of our different days of notes, so things like how is light produced, and we talked about the quantum mechanical model, and we talked about light and energy calculations, and then the extra topics from today. So all those notes should have questions, CASTA questions and summaries written. Those things help you process the information and see if it made sense. There was a reading on exceptional electron configurations, and then there was unit practice problems. That was kind of the assigned work. The assignments worth points, there was just 2 of them in this unit, the flame test lab report and the electron configuration practice assignment. So make sure those things are done. Get any help on them if needed. And then I just want to make sure, again, if you're watching this video related to my class in trimester 3 of 2021, the Unit 7 quiz will be assigned on Thursday, April 1st. So just know that that's coming up. And so if you have any questions on any of the topics from this unit, you can look in the unit plan. It lists all of the objectives of things you should be able to do now that this unit is done. You can use that as kind of a checklist to see if you have any questions or things you need help with before you take that unit assessment. And just remember, I have office hours Monday through Thursday from 2:15 to 3:15 on Zoom, and Fridays from 1:30 to 3 o'clock on Zoom. Thanks so much for learning more about Doppler effect and lasers and photoelectric effect with me. See you next time.